Yeah, so I wanted to talk today about Gaussian process regression and in particular convergence properties. So the outline of my talk is very simple. So I'm going to start with just the problem formulation, so just telling you what problem I'm trying to solve. And then I'm going to tell you how to solve it using Gaussian process regression. Then I'm going to tell you how well that works. So what kind of convergence properties, results, and accuracy you can expect when you do solve this problem using Gaussian process regression. And then in the end, I'll just have some conclusions. All right, so the problem that I'm trying to, that I want to solve is this one. So I have some function f, so I have some unknown function f. And what I know about this function is I have some function evaluations, so I have some points un in my domain u and corresponding function values. And from those function values, I want to reconstruct the underlying unknown function f. Okay, so that sounds like quite a simple problem, but I think I don't need to convince the people in the audience that it's not as easy as it looks, and that it actually has a lot of applications as well. Right? So that's the problem that I'm interested in. I'm going to solve it using a Bayesian statistical framework. So that is going to give me a probability distribution on my unknown f, conditioned on this observed data in the form of function values. So that is known as what is known as the posterior measure. So in this framework with the Bayesian statistical setup, I don't just get one reconstruction of my function f, I actually get a whole probability distribution on f given the observed data. So that is going to allow me to do some uncertainty quantification as well in this recovery process. Right. So that is the setup, what I want to do. What I'm then interested in is convergence as n tends to infinity. So in particular, as the number of function values that we have, n, if that tends to infinity, do we actually recover the true function f? Okay. So that is, in this Bayesian statistical framework, that is a form of posterior consistency. So in particular, what I'm going to look at is if the mean of my posterior converges to the true function f, and if the variance of the posterior goes to 0. Right? So if this is the case, then this probability measure that we get on f given y, then we know that the mean of this actually recovers our true f, and the variance goes to 0, and so we recover the true function f in that setting. Okay, that is the problem. As I said, I'm going to solve it in a Bayesian statistical framework, and in particular, Gaussian process regression is just a particular instance of this Bayesian framework where you choose all of your distributions to be Gaussian distributions. So it's a standard Bayesian procedure. So what you do is you choose a prior distribution on the unknown f that you want to learn. The way that you choose the prior is, again, in any application, dependent on that application. So you have to incorporate any information that you have about your unknown function f. Okay. I'm going to come back to that point later on. So as I said, the distribution that you choose here is a Gaussian process. If you're not that familiar with Gaussian processes, I've given you the definition here, so that you put a Gaussian process prior on f means that under this Gaussian process prior, the function f evaluated at any point ui in your domain is a Gaussian random variable. So in particular, this vector here follows a multivariate joint Gaussian distribution. And the two inputs that we have here, the first one is a mean function. So I've chosen mean 0 here for simplicity, but everything that I'm going to say in the talk also holds for non-zero mean. So the mean just gives you the mean function, so the expected value of f at ui, and then the covariance kernel k that you have here gives you the covariance between two different points. Right? So the k evaluated at some points ui and uj is going to give you the covariance between f at ui and f at uj. Okay, so this is the mathematical definition. More visually, you have something like this. So here I've given you an example just in 1D. So if you just have a one-dimensional function f, Then by putting a Gaussian process prior on it, you impose some mean, which is the black line here. So here impose some mean 0, and then you're going to have some fluctuations around this mean. So here we've got a standard deviation of 1, for example. So what this does is it poses some distribution on functions, and the different realizations or sample parts of the function are going to look something like this. So they're going to stay close to the mean 0 that we have imposed, and then the fluctuations that you get in either direction depends on how large you've introduced the variance or the standard deviation. All right, so that is the first step. So you put this Gaussian process prior on F, and then as usual, in the Bayesian setup, you then get a posterior distribution, which is just the prior distribution that you imposed, conditioned on your observed data. So again, my observed data Y here was the point values. So I have these point values, which are indicated here, say at these points here. So because you're using Gaussian processes, this conditioning can actually be done explicitly. So that is one reason why Gaussian process regression is so popular. General in this Bayesian framework, you can choose any prior distribution that you like, but if you do choose a Gaussian prior distribution, then you can actually compute the posterior explicitly. So it's again a Gaussian, and you also know the mean and the covariance function explicitly. So I've given you the formulas here, but they're not really that important. What is just important is that you can actually write these down explicitly. Okay, so then you again get some mean function, which is now a function that goes through the points where you know that your function goes through, and then you still have some fluctuations in the other parts where you don't really know what your function is, and again you get some sample parts. All right, so that is what Gaussian process regression is. So this is how you get your posterior distribution on your unknown function f given y, given the observed data y. So again, you might think that, I've told you how to compute this, so you might think that you're done. So the difficulty in applications is often actually choosing this prior distribution, right? So once you have your prior, I've told you how to get the posterior, but how do you actually choose this prior, right? So as I said, the way that you have to choose the prior is that you have to incorporate any information that you have on your function f, right? So in particular, the prior determines a lot of different properties. So the way that you choose the covariance kernel K in this setting will, for example, determine how smooth you assume that your function f is. So what I mean by that is how many derivatives you have. So here I've shown a couple of different examples. So I know you can't read the labels, but the labels are not important because I haven't really told you how to interpret the labels. So you should just look at the figures. So for example, in the first row, these are samples from a Gaussian process where the paths are just Hölder continuous with exponent 1/2. So they're not even differentiable, so they look quite rough. Whereas this row here has samples which are analytic. So these are C infinity functions. So you can impose different smoothness. You can impose different contrasts. So by contrast, I mean the variation that you get in the horizontal direction. So whether you have very large fluctuations or only very small fluctuations. And then also length scales, which are more like vertical length scales rather than the horizontal length scales. So for example, in this figure here, you can see that you get samples which vary only on a very long length scale. So here you have quite a long typical length scale of fluctuations, whereas in this one here, you do fluctuate on a much shorter length scale, and so you have shorter length scales here. Okay? In general, it also incorporates a lot of other properties, such as whether your function is periodic and whether it's stationary, but I'm not going to talk too much about those today. Okay? So today I'm going to focus on things like this. So the problem is then that properties such as the smoothness and the contrast, so the size of the fluctuations and the length scale of the fluctuations, that is something that you typically don't know, right? So all you know about your function f is these function values that you had, and you don't typically know what the smoothness is or the contrast of the length scale. So then it's actually difficult to choose a prior and Yeah, so you wouldn't really be able to choose what these things are a priori. Okay, so usually the way it works is that once you've chosen your kernel K, then the kernel K will have some hyperparameters in it that will govern what these different things are. Okay, so I'm going to show you an example later on. But there's typically, for example, just a scale, a hyperparameter, say lambda, which exactly corresponds to this here, whether you, so when lambda is large, you get large scale fluctuations. And when lambda is small, you get small scale fluctuations. Okay, so there's typically some hyperparameters or just parameters in the kernel K, which govern what these things are. Okay, so because we don't know what they are, we are going to follow an empirical Bayes approach. Okay, so we could do a proper hierarchical Bayesian approach. The problem with the hierarchical Bayesian approach is that you would have to integrate out the unknown hyperparameters, and that is typically very difficult to do. That can be computationally very expensive. So a bit cheaper version is the empirical Bayes approach, or also known as a plugin approach. What you do there is you try and estimate what the hyperparameters are. So any hyperparameters theta that you know you need in your covariance kernel K, you would estimate them from the function data that you have. So say you need to estimate this length scale parameter, on which length scale your function f typically fluctuates. You could learn that from the data that you have. Okay? And then you just take this estimate that you have, which would be this theta hat n, and then you just plug that into your posterior. Right? So you take the posterior distribution that is derived under the assumption that you know what the hyperparameters are, and then you just pretend that you do know what the hyperparameters are and plug this in as kind of the true value of the hyperparameters. Okay. So that's what the empirical Bayesian approach is. So then you just get this posterior, which is the GP with the mean and the covariance function that I showed you earlier, and then you just plug in this estimate that you have of your hyperparameters. Okay. The way that you estimate them doesn't really matter for the analysis that I'm going to show you. So there's very many different ways that you can do it. You can do maximum likelihood, maximum a posteriori estimation, or something like cross-validation. All of that is valid, and all of that could be used. And as I said, the results that I'm going to show you are independent of how you actually compute these estimates. Right. So then going back to the question that I would then want to answer is, do we actually get posterior consistency if we do this? If we just do this empirical Bayes and estimate the hyperparameters, what kind of conditions do we need? So do we kind of get convergence of this methodology as n tends to infinity? Right. That is the question I want to answer. Right? So we want to look at the limit as the number of data points that we have, the number of function evaluations tends to infinity. And again, what we want to show was this posterior consistency, which in this case means that the mean of the posterior that we get on f tends to the true function f. So the posterior mean tends to the truth, and the variance tends to 0. Okay? So this is the variance of the posterior on f. Okay? So that's what we're going to show. So it turns out that we can use some results from numerical analysis or approximation theory. So essentially, what you use is these two properties that you have. So if you look at the mean, right, so this is the mean of the posterior on f. Okay. So you can use the explicit formula. So I told you there is an explicit formula for it, right? So you can look at that formula, and what you see is that one, it can be written in this form, right? So what this means is that the mean m is a linear combination of kernel functions. So you have this kernel k here, which was the prior covariance kernel, and then the m is just a linear combination of these functions k, where the coefficients alpha are known. And the second thing that you have is that it is an interpolant. So if you look at the points UN, so these are the points where we had our training data Y, okay, then you recover the truth, right? So that is because we are conditioning on the data, right? So you see that the mean always goes through the data points because we're doing this conditioning, and you can also see it explicitly from the expression. Okay, so these two things tell you one thing, well, two things. One is that we have an interpolant, so the posterior mean is always an interpolant of f, and it's interpolant with the basis functions k. Okay, so the k here take the role of the basis functions in the interpolant, right? So the mean is what's called a kernel interpolant, just means that it's an interpolant with kernel functions as basis functions. And in particular, if you choose the kernel as an isotropic kernel, so that means that the kernel only depends on the Euclidean distance between its two input arguments, then the mean is actually a radial basis function interpolant, right? So radial basis function interpolants, or more general kernel interpolants, that is something that has been studied a lot in approximation theory, right? So there is actually a lot of information about what happens as n tends to infinity, and so you can use this theory to then apply this to Gaussian process regression. Okay. So there is theory available for a very wide range of choices, so for a very wide range of choices of k, for example, and the convergence properties that you get will depend very much on the specific choice of k that you choose. Right, so that makes sense. So if you think about it, as I said, the k that you get are the basis functions. So the basis functions that you use in your interpolation, that is going to have a very big effect on how well your interpolation is doing. Okay, so I'm now going to show you two particular choices for k, which are very frequently used, and then we'll see what happens when n goes to infinity. Okay. So the first example is the family of Maternal covariances. So this is a parametric family of covariance functions. You have one parameter, so three parameters. One parameter is the sigma squared, and that is the marginal variance. This is the one that governs the contrast, so the one which governs how large your fluctuations are. Then you have what's called a correlation length lambda. So that gives you the fluctuation length scale, so the typical length scales on which your field varies, so the vertical kind of typical length scale. And then the third parameter is the parameter nu, which is the smoothness parameter. So the nu tells you how many derivatives your sample paths are going to have. And typically, let me get it right. So I think if sample parts of this process are going to have nu derivatives, right? So the nu corresponds directly to the number of derivatives. So the general formula looks a bit horrible. So you have the gamma function here, and this is the modified Bessel function of the second kind. It does simplify a little bit for specific choices of nu. So in particular, if you have the smoothness nu equal to 1/2, so then you get functions which are Hölder continuous with exponent 1/2. It simplifies to just this exponential function here, where you don't have the sigma squared and the lambda. So you might recognize this as the covariance function of the Ornstein-Uhlenbeck process, if you're familiar with that. And when nu equals infinity, or in the limit, as the smoothness nu tends to infinity, you get the Gaussian covariance function, which then has, so the only difference between these two is that you have a square in the norm here. So this one is a lot smoother, and this one actually then gives you sample paths which are analytic, so C infinity sample paths here. Okay, but in general, it's a very flexible family, which can give you very many different ranges of behaviors, and the hyperparameters theta that I was talking about earlier would now be the smoothness lambda, the fluctuation length scale, sorry, the smoothness nu, the correlation length lambda, and the variance sigma squared. Right. To formulate the convergence result, I have to define these two quantities here. Okay, so these are two quantities that are related to how you choose the what's called the design points, so the points at which you gather your function evaluations. And so these were the points where we were given our function evaluations of f. Okay? And both of these things, the h and the rho, depend on n. So the first thing is the fill distance. Fill distance is something that decays with n in the optimal setting, the best rate, and well, for most point sets is that it goes like 1 n to the minus 1 over the dimension, right? So the parameters, the domain U here was a domain in the Euclidean space of dimension du. So the du is the dimension of my input u. Okay? And the fill distance is this thing here. So you look at the supremum over all points in your domain U, and then the infimum over all design points, and then you take distance. So the fill distance measures how space filling your design dn is. Right? So the fill distance, you can interpret it as the radius of the largest ball that you can fit in U, which does not contain any of the design points. Okay? So if the h is small, then your design dn is quite space filling, and you kind of, it measures how well you cover all of U. Okay? Then the other thing is the mesh ratio. The mesh ratio measures how uniform your points are spread. Okay, so the mesh ratio at the top, you actually have your fill distance. Right? So you have in the denominator the fill distance again. It's the same here. And then in the denominator, you actually have the minimum distance between two design points. Okay? So in a way, you kind of taking the ratio of the maximum distance between the two design points and the minimum distance of two design points. So that kind of tells you a bit how uniformly the points are spread in your domain U. Okay? If you have really a completely uniform design, then the mesh ratio will just be equal to a constant. If you don't have a uniform design, so if you have a design that does fill your space quite well, but also has points which are very close together, then the rho n can actually be increasing in n, right? So this is something that can grow in n as well, if you don't have a very uniform point set. Okay, so with those things, we can then give the error estimate. So I know it looks a bit complicated, there's a lot of things to take in. So let's look at all the different things. So this is an error estimate now for the difference between my true function f and the mean of the Gaussian process posterior. Okay? And I can show in L2, this can be bounded in terms of this thing here. Right? So we have general constant. For f, this is an estimate that holds for any f of a certain Sobolev smoothness. So that essentially comes from the fact that you're using these Maternal covariance kernels, and the reproducing kernel Hilbert spaces of the Maternal covariance kernels are these Sobolev spaces. So you have this Sobolev space here. If you're not familiar with Sobolev spaces, this is kind of assuming that f has mu plus du over 2 derivatives, which are square integrable. Okay, so it's an assumption on how smooth your true function f is. Okay? And then you have these two terms here. So one involves the fill distance and one involves the mesh ratio, which is why I introduced them on the previous slide. And then you can see that the rates that you get really only depend on the smoothness parameter. Okay? So the lambda and the sigma squared that we had actually only go into the constant. So how you choose this correlation length and how you choose the contrast, that only goes into the constant. What influences the rates is only the smoothness. So that's something that you might expect, how many derivatives your f has and how many derivatives your basis functions have. And that's what's going in. So the nu here, as I said, is kind of the true smoothness of f. Right? So the nu depends on how smooth your true f is. And then the nu star is how how well what you're estimating the smoothness to be. Right? So this is your estimated smoothness. Okay, so you get something here which converges. So as I said, the fill distance is decreasing in n. So this is something that decreases, and then here the mesh ratio could be increasing, so you might possibly get a penalty here. When you're estimating the smoothness correctly, so when your estimated smoothness actually is the true smoothness, then you actually get optimal rates. So this is the rate that you get, and they're optimal in the sense from information-based complexity. So if you look at the optimal rate that you could approximate any function f with this smoothness based on n function evaluations, then that is exactly this rate. So it is optimal. When you're overestimating the smoothness, you might have to pay a penalty when the set is not quasi-uniform, right? So this thing here decreases in n, so this gives you a rate. The problem with point sets which are not uniform is that this row could be increasing in n, and so if your estimated smoothness is greater than your true smoothness, then this kind of is like a penalty that kind of knocks off a bit of the convergence rate. Okay, so again, that makes sense. So if your estimated smoothness is larger than the true smoothness, what this means is that the basis functions that you're using, so remember the new star, right? So the new here, so the new star would correspond to the smoothness of the basis functions. So if the new star is greater than nu, then the smoothness of the basis functions that you're using to approximate f is greater than the actual smoothness of f. And so the basis functions are kind of too smooth. You're trying to approximate a not so smooth function by smooth basis functions. And that's where you get problems if the points are not quasi-uniform, because it's really at the very small scale that you see how many derivatives you have. Okay. So this result is, I was very surprised how little assumptions you need on the estimated hyperparameters. So essentially you just need them to be bounded between 0 and infinity. So essentially whatever you choose and whatever you estimate, you still get convergence. So you might not get optimal results, but you are really pretty much always going to get there eventually with reconstructing f. No matter what you choose. You don't need convergence, so I've written down the theorem here in a bit simpler form with convergence, but you don't need these parameters to converge, and you can work with the lim_inf and the lim_inf and the lim_sup if you don't have convergence. Okay, but the takeaway here is that you really don't need any assumptions really on how well you are able to estimate the hyperparameters. And then there's a similar result also for the standard deviation of the posterior. All right. So one problem with these results is that you do get quite bad dimension dependence. So you see that in the rates here, you do get the 1 over dimension factor here. And I mean, that is essentially due to your assumption here that the f is in this standard isotropic Sobolev space. So as I said, for this class of functions, this is actually the optimal rate, so you can't really do any better. Okay. So the next result I'm going to show you is going to be a result which is a bit better in higher dimensions. So if the dimension du is very high, then this would give you very slow rates. And essentially the crucial thing is that you have to change the class of functions that you're dealing with here. Right? So the setup is quite similar. Okay, so the crucial thing is that you move from standard Sobolev spaces that we had here, this standard isotropic Sobolev space, and you move to these Sobolev spaces of dominating mixed smoothness. Okay, so these correspond to tensor products of one-dimensional Sobolev spaces, and these are much smaller spaces, and you have a lot more control on the mixed derivatives, which is why they're called spaces of dominating mixed smoothness. Okay, the setup is otherwise quite similar. So instead of a Maternal kernel, So the family that I showed you before, what you do is you use what are called separable or tensor product Matern kernels, which are just products of one-dimensional kernels. And kind of makes sense because you're working in this tensor product of one-dimensional spaces. Then you do need a very specific setup for the design points. So for the points where you get your function evaluations, that is now chosen specifically as a Smolyak sparse grid. So before we didn't have any restrictions on what the point set was. We just had our fill distance and the mesh ratio, and then that worked. This is a very specific setup where you now use these Smolyak sparse grids. And I didn't want to write down the full result in full detail because it gets a bit long and a bit complicated. But essentially the crucial thing is that in this setup, you can actually very much improve on the dependence on the dimension. Okay? So you can show that you get a rate which is dimension independent up to the log factor here. And so the dimension does appear in the log factor of n, but the rate that you get in n actually only depends on the smoothness of your function f, the how many derivatives your true function f has, and then what you're estimating. So the new star would then be the smoothness of your basis functions in the kernel. Okay, so up to the log factor, you get something that is dimension independent. If you're estimating the smoothness correctly, then this is the rate that you get. Okay? It is optimal up to log factor. So the theory from an information-based complexity isn't as well developed in these cases as it is before. So you're not really 100% sure whether this is optimal because nobody really knows what optimal is. But so far, the best results that have been shown are exactly this with a slightly different log factor, but the results that you get, the rates that you get in n in this term here are definitely the optimal ones. Okay? As I said, this does require a lot stronger assumptions on your function f. And that was really all I wanted to say. So I think I'm already a bit over time, but let me just reiterate this. So what I showed was that how you can use Gaussian process regression to determine a posterior measure on an unknown function f, given n function values. And then I showed you that you do get posterior consistency in really a very wide range of cases. So you don't need very many assumptions. And in particular, this methodology seems quite robust to prior misspecification and learning of the hyperparameters. And if you're interested in more details, then there's this archive preprint here.